Welcome to your first vectors lesson. This is the introduction to vectors. Today we're going to be learning mostly a lot of definitions and notations involving vectors. As you can see, the objectives are recognizing whether a quantity is scalar or vector, use different representations of a vector, calculate magnitude of a vector, determine if vectors are parallel, write the position vector of a point, and then calculate resultant vectors. So let's just get started. So your first thing here is the vector basis. Just understanding what a vector is. A vector is just something that has both size and direction, or magnitude and direction. A lot of things that are vectors or can be represented as vectors are things like displacement and velocity. A scalar, on the other hand, or in comparison or in contrast, is a quantity that has size but no direction. So examples of scalars are distance and speed, those things, temperature, weight, all right? Vectors are represented visually by arrows, where the length of the line indicates the size or the magnitude of the vector, and the arrow shows the direction. The vector shown here at the side, AB, it can be written as capital A, capital B, if you're going between the 2 points with a symbol that looks like a ray symbol above, or just with the capital A, with the lowercase a bolded. So again, you can either label it with the capital letters at the ends of the vertices, or at the end of the vector. The letter at the beginning goes first, the letter at the end goes second, obviously. Or again, you can use a small bolded letter. And again, a way of representing or writing the vector is in what's called a column vector notation. And for example, this vector is represented by 3, 4. In general, the column vector is x, y. So it's your x movement over your y movement. All right. So again, obviously, your movement is based on the coordinate grid. So here you're moving 3 units to the right and 4 units up. Hence +3, +4. Unit vectors, a special type of vector. The thing about unit vectors are that they have a magnitude of 1. And so their overall length is 1 is what that means. All right. So when we describe unit vectors, for example, along the axes, all right, so the x-axis and the y-axis, we use I for the x-axis, we use J for the I for the x-axis, J for the y-axis, and later on we'll introduce the third dimension, Z, and we'll use K for the z-axis. We do also call the unit vectors base vectors. And again, as you can see, in 2 dimensions, the vector that moves along the x-axis is 1, 0, like this, or in 3 dimensions, 1, 0, 0. The vector that moves you along the y-axis can be represented as 0, 1, or in 3 dimensions, 0, 1, 0. Again, all it's showing is that you're moving 1 unit, for example, with the vector I, you're moving 1 unit in the x direction, but 0 units in the y direction. And also, if you extend it to 3 dimensions, 0 units in the z direction. Okay. And same thing with J. You're moving 1 unit in the y, but 0 units in the x direction. So obviously, it has a length of 1. And then also, if you extend it to 3 dimensions, 0 units in the z direction. And then obviously, the unit vector for movement in the z direction is given by k, and that is the vector 0, 0, 1. And again, any vector can be written in terms of its movement in the x, y, and z directions, and that would be given in terms of I, j, and k. So again, for example, the vector from the previous slide is vector AB. Its column vector form is 3, 4. That translates to the vector 3i plus 4j. So here's a column vector form, and here's your ij form. And again, once we get into 3 dimensions, we can also have a k component. Again, just talking a little bit more about the magnitude of vectors. Again, if we use the example of the vector AB that we've been talking about on the previous page, okay. This is vector AB. It was represented by movement of 3 units in the x direction, 4 units in the y direction. And if magnitude is just the length, this goes back to basically triangle trig, and we can figure out what the magnitude or the length of AB is. So AB, again, the notation for AB is the absolute, the notation for magnitude is the absolute value bars. All right, so now when you see that on a test or a quiz, you need to know that you're being asked to find the magnitude. So the magnitude of AB, though, will now be the root of 3 squared plus 4 squared, which is obviously the root of 25, which can be written as 5. So the length of the vector AB itself is 5 units. So that's its magnitude. And the other interesting thing here is that Pythagorean theorem can be extended to the third dimension, and the formula, if you want, for the magnitude of a vector in 3 dimensions is just the root of a squared plus b squared plus c squared. And those of you who write SAT, again, that's the length of a diagonal in a box or a right prism from one corner to the diagonally opposite corner through the box. So quick way to calculate that length. All right. And then once you have the length of your vector, you can multiply it by a constant to change its length, and that's called just the scalar multiplication. So if I wanted the vector AB to be 10 units long, I would multiply by 2, obviously. And obviously the size of the components would change as well. All right. Okay. Equal and negative vectors. 2 vectors are equal if they have the same direction and the same magnitude. I think it's obvious, they have to be identical. One thing that's important to know too about vectors, and the graph here on the left shows it, but equal vectors can be anywhere in space. All right, they don't have to be in the exact same location. So in this case, AB does equal PQ, because again, their movement is the same, but that location can be anywhere in space. All right. So again, as long as the movement is 2, 5. So here we move 2 units in the x direction, 5 units in the y direction, and it's the same. This vector for PQ, 2 units in the x direction, 5 units in the y direction. 2, 5. And here as well, 2, 5. All right. Negative vectors do have the same magnitude, but they're opposite in direction. So the picture on the right here, vector AB is moving up and to the right. The vector MN is moving down and to the left. And again, notice when the vectors are written or expressed, you're starting from the tail of one vector to the tip. All right. So AB or MN. Okay. And again, an important note too, you can change, or you can write vectors in terms of their opposite. So for example, the vector AB, written here, can be written as a negative BA. BA will automatically change the sign of the components, and then putting the negative in front will again change them back. So you will get the same vector. Parallel vectors. Parallel vectors are 2 vectors are parallel if one is a scalar multiple of the other. So again, that means if you can multiply the length of one by some quantity and you get the length of the other, they're parallel. All right. As long as their components are in that same scale factor. All right. So again, here showing on this vector AB. Components are 2 and 5, and vector CD here, its components are 4 and 10. And again, obviously, the overall length of AB, or the length of CD will be twice that of AB. And likewise, EF. EF, it's 1 unit in the x direction and 2.5 units in the y direction. So again, it's half the length of vector AB. And again, all the vectors are given in their component forms here, and we can see that we can see what their scale factor is in comparison. So CD is equal to double AB, and EF is equal to half of AB. Again, they're just scalar multiples of each other. Just little thing to add here would be that K can be an element of the reals. K can be any real number. Okay. Position vectors, a special type of vector. They get used quite a lot, so it's very important that you know and understand them. Position vectors are vectors that start from the origin. All right. So in this way, when you know a coordinate of a point, that point can be expressed as a position vector. So for example, in the diagram here, we have the point P. Its coordinate is -5, 12. All right. So automatically we can express it as a position vector. And the other thing with position vectors, the first letter is always O because we're starting at the origin, and it goes to whichever point we're talking about. So in this case, it's OP, and our movement to get there is -5 in the x direction, 12 in the y direction. And again, it can also be expressed as -5i plus 12j. And so those are position vectors, and we do use position vectors quite a lot in finding other vectors. All right, and again, it's mentioned or said again in the orange box at the bottom. All right. And now the last thing here is just the resultant vectors. The resultant is how you move from one point to another. So for example, in the diagram here, we want to go from A to B, and you can probably find by the coordinates. The coordinates of A are 2, 3, given. Let's mark it here. And the coordinates of B are 6, 6. Okay. So obviously you can probably figure it out just by logic and thinking about it. To get from A to B, you have to go 4 units in the x direction and 3 units in the y direction. But there are some formulas associated with this. Not in the formula booklet, however, but you do need to know them. So a way that we can get from A to B is, and then this you have to see a little bit differently here. We're going to use the position vector. So, but to do that, we're going to go from A to O. So we're going to go this way, and then we'll go from O to B. So from O to B this way. And today we're just going to talk about the algebraic addition of the vectors. Next day we'll talk about the geometric addition. But in order to add vectors algebraically, you need to have the same letter. They need to pass through the same letter, or the same letter needs to be adjacent in the equation. So for example here, that's why we're going AO plus OB. Okay, AO plus OB. And so when you think of it, AB is equal to AO plus OB, it's like the O's almost cancel each other out. But you must move through that same point. So the vector AO is given by, if we figured out what AO was, how to get from A back to O, it would be -2, -3. And if we add the vector OB, the position vector OB, that's already 6, 6, we know that. So if we add those, all you're going to do is add in the rows of the column vectors. So -2 plus 6 is 4, and -3 plus 6 is 3, and that gives us the column vector 4, 3. Remember what we talked about is that the vector AO can also be, its letters can be reversed, and that can give us -OA. So that's exactly the same as AO. And then what we usually like to do is we like to rewrite it and put the negative vector second, and so that gives us this last form of the equation right here, where AB is equal to OB minus OA. And if you put the vectors in there at that stage, the vector OB is still its position vector 6, 6. And if we subtract the position vector of OA, the position vector of OA is simply its point, so 2, 3. When we do that subtraction, now again we subtract within the elements, or the components of the column vectors, I should say. So it's 6 minus 2, which is 4, and 6 minus 3, which is 3, which also gives us the column vector 4, 3, how you get from A to B. And again, if you want, there's a little formula here. Again, it's something more that you say in words and that you need to know. All right, this is simply said as position vector of the second point. And that's the second point in the vector. And it's minus the position vector of the first point. So you'll hear your teacher say that very often, and it's very often asked as a first question in a vectors question on an IB exam. It'll just ask you for the vector between 2 points. You need to know that it's the position vector of the second point in the vector notation minus the position vector of the first point in the vector notation. So now make sure you go and practice some of these questions and ask questions if you have them. Thanks.